Hi guys, in this video we are going to look at some trends in atomic properties that can be viewed when we're looking at the structure and organization of the periodic table. Now, when the end of the previous lecture, when we were looking at electron configurations, we already got a feel for the reason behind some of the structuring in the periodic table. Specifically, we introduced this concept of the S block, P block, and D block elements, and saw how we can classify these different regions of the periodic table based on the outermost orbital in which we are placing electrons. So the first two columns are placing electrons in s orbitals. This central set of 10 columns places electrons in d orbitals, and the final 6 columns place electrons in p orbitals. And we can see that the periodic table naturally groups these sorts of elements together, making our s, p, and d blocks. Now, it turns out that there are a lot of other interesting trends that fall out of this arrangement of the elements, as illustrated here. The first trend that we're going to talk about is a trend in atomic size. So recall that if we, for example, move down one of the columns in the S block, we are moving to higher principal quantum numbers, n equals 1, 2, 3, 4, and so forth as you go down those rows. And we recall from our lecture on orbitals that as you move to higher values of that principal quantum number n, the size of the orbital increases. So going from 1s to 2s to 3s results in larger orbitals. So the first trend then that falls out of this organization of the periodic table that we're going to talk about is a trend in atomic size, where the atomic size increases as you move down the periodic table, down any given column. Right? And this is simply a manifestation of having placed more electrons in these larger orbitals, orbitals with a larger principal quantum number n. Okay? So first trend, atomic size increases as you move down the periodic table. Now, it turns out that the atomic size actually decreases as you move from left to right. So the details of this are a bit beyond our introductory coverage of the topic, but it really boils down to the fact that when you're moving from left to right, you are fixed essentially with a certain type of orbital. For example, if you're going across a column and you have principal quantum number of 2, say in the second row, then we're dealing with 2s and 2p orbitals. And when you move from left to right, though, you're introducing a greater degree of nuclear charge. So you're still dealing with the same type of 2s and 2p orbitals, but the larger nuclear charge that occurs as you move from left to right across the periodic table results in a contraction of that orbital size. The larger number of protons pulls those electrons in closer, and so we see a decrease in atomic size going from left to right, and then our increase, as we said, going from top to bottom. Okay, now our next trend that we want to look at actually requires us introducing another definition before we jump into it. So I'd like to take a minute here and introduce this concept of electron shells. So an electron shell is a group of orbitals with the same principal quantum number n. So the first n equals 1 shell is comprised of only the single 1s orbital. Because remember, in the principal quantum number 1, we're not going to see any p orbitals or d orbitals. The only thing there is s orbitals. So that's a lonely shell. But when you move to n equals 2, then you have the opportunity to have both s and p orbitals. And so all of the 2s and 2p orbitals collectively form the n equals 2 shell. And so on and so forth as you move to higher and higher energy orbitals. So every time you move down a row on the periodic table, electrons are being placed in a new shell. Okay? And that shell in which you are putting those outermost electrons, those highest energy electrons, we have a special term for that. We call it the outermost shell. So the outermost shell for a given atom is that shell containing electrons with the largest principal quantum number. So we could label the outermost shells on the periodic table by simply numbering the rows. So if you look at the first row here, the outermost shell is going to be an n equals 1 shell. The second row here, the outermost shell, is going to be n equals 2, n equals 3, and so on. Where again, we are going to be focusing on just those s and p block elements for our introduction here. Okay, so now the question I want to ask though is, why is it that I am calling these orbitals, this shell with the largest n, the outermost shell, or the outermost collection of orbitals? So I want you to pause the video for a second and answer that question. Maybe you look back in the notes and find some justification for why the outermost shell would have the largest principal quantum number n. Okay, so hopefully you found something or came up with some sort of argument related to the size of these orbitals. So once again, we recall that the orbital size increases as you increase that principal quantum number n. And so as a result, if you pick that largest value of n for the outermost shell, then you're effectively picking the largest orbital, and it's going to be the orbital then that's effectively on the outside, sort of surrounding the whole atom. Okay, so now I'm going to introduce a general principle that's going to use our definition of outer shell and allow us to kind of lay the foundation for our very important periodic trend that we'll talk about shortly. So the rule here is that atoms have a tendency to prefer to have a full outer shell. Okay? And so if we look, for example, here at the energy diagram for neon, we've got 10 electrons. Okay? So neon puts 10 electrons and completely fills up its outermost n equals 2 shell. Right? So the n equals 2 shell is full. Right? And so notice neon corresponds right over here to this noble gas. So another way of saying this is that atoms essentially want to look like the closest noble gas. All the atoms want to look like a noble gas. Okay? So in the case of hydrogen here, this hydrogen atom tends to want to look like a helium atom. So he'll want to get another electron some way, somehow, in order to get that full outer shell to look like neon. All right? When you're looking at second row elements that are near neon over here, so for example, nitrogen, oxygen, or fluorine, all of these guys, they're going to have a tendency to gain electrons in order to look like neon. So for example, if we say, took the electron configuration for fluorine, right, then we would say, well, hey, in order to get to look like neon, I would have to add an additional electron. Okay, so the same sort of argument holds for these other guys. Now, you can go down a row and you can look at, phosphorus, sulfur, chlorine. All those third row p block elements over here near argon are going to want to, once again, gain electrons to look like argon. Now, something interesting happens here. Remember that the principle that we're following here is that atoms want to look like a noble gas, but they're going to look like the nearest noble gas. So if we scale back and we look at one of the lighter elements, lithium here in this example, neutral lithium has exactly 3 electrons. Okay? So then the question we want to answer is, what's going to happen to this second row element, lithium, right, in order to get a full outer shell? Well, there's 2 options. One option would be to gain 7 electrons to look like neon. Then you'd have to come in here and gain 1, 2, 3, 4, 5, 6, 7 electrons, which is obviously is a lot of work. But remember, what neon or what lithium is going to do is not just go after neon because it's also second row. It's going to look for the shortest pathway to look like a noble gas, which in the case of lithium is not at all to do anything with neon, but actually to go ahead and remove this outermost electron in the 2s orbital to get a helium electron configuration. And so we have some shorthand notation that we use to denote the electron configuration. In this case, it would be lithium plus. We denote the electron configuration by putting the noble gas, right, with the corresponding electron configuration that matches the ion in brackets. Okay, so we read this as lithium plus has the same electron configuration as helium. Okay, so let's work out the example I mentioned before. So remember, if we take, for example, fluorine, which has 9 electrons, and we want to predict the most common charge that fluorine is going to obtain, well, we are going to look at fluorine and say, what's its closest noble gas? As we said previously, that's going to be neon with 10 electrons. So then we're going to say, well, fluorine is going to be most likely to gain an additional electron and then look like neon. Okay, so if we were to write out the electron configuration of the corresponding F- ion, it would just be the electron configuration of neon. So we write neon, the chemical symbol, in brackets. Okay, so now if we go down a row on the periodic table, look at sodium here. Sodium has as its outermost electron the single 3s electron. And what we end up doing now is asking the question, we want to determine what the closest noble gas is if we are going to determine the common ionic charge. So for sodium, once again, the options are gain 7 to look like the noble gas across the same row, argon, or sodium could simply lose that outermost 3s electron, right? And then form, of course, a sodium plus ion that would then have the exact same electron configuration as neon. And so a way that this general principle is oftentimes laid out is in the context of the so-called octet rule. So if you notice that a lot of the elements that we're working with here, so in fact all of these guys, right, this guy as well, and all of these guys, and we're not really going to be concerned with carbon for our discussion here. All of these guys circled in black will tend to find the nearest noble gas and satisfy a so-called octet. In other words, there will be a total of 8 electrons in the outermost shell, right? And the 8 electrons correspond to the filling up of both the s and p orbitals holding 2 and 6 electrons respectively. Okay. Now, the octet rule does not hold for these lighter elements like lithium, beryllium, and hydrogen. Okay, because remember, in those cases, the closest noble gas is in fact helium. So lithium and beryllium, and would also be hydrogen, are really going to be forming what's sometimes called a duet, right? And or 2 electrons, but they're just different terms to represent the same fundamental concept. All atoms want to end up looking like that noble gas. All right, so here's our periodic trend then. Right? Because of how the periodic table is structured, if you look down a given column, all of the elements in that column will have a tendency to form an ion of a certain charge. So fluorine and all the halogens will tend to grab 1 electron to look like neon, argon, krypton, whatever. Oxygen, sulfur, and these guys will tend to grab 2 electrons to look like argon, beryllium, or argon, or krypton, or xenon, right? And so on and so forth, right? Nitrogen, you'll want to grab 3, phosphorus 3, arsenic is 3. And the compounds over here on this side will want to gain, or lose rather, 1 and then 2 to come all the way back to look like neon. Okay, so because of that orientation in the periodic table here, right, we can nice and easily group all of these common charges by just remembering what column that given element lands in, and then count off how many electrons must be gained or lost to get to the nearest noble gas. Okay, the next periodic trend that I want to mention here can help. You can actually look at the previous trend to help us remember this next one. So the next trend is called electronegativity. Kind of a big word there, but basically what electronegativity is a measure of the tendency of an atom to attract electrons. Okay, so if you have a higher tendency to attract electrons, you have a higher electronegativity. And so if you look at the periodic table here, we find that these atoms over here on the far right have a tendency to gain electrons, whereas the atoms over here on the right-hand side, or the left-hand side, have a tendency to lose electrons. So these guys, lose electrons. These guys gain electrons. And so this trend in electronegativity actually follows this general pattern. So it'll help you remember it. It turns out that atoms on the right-hand side of the periodic table do in fact have a larger electronegativity. So electronegativity increases as you go from left to right, and electronegativity decreases as you go down the periodic table. And again, this is a manifestation of the fact that you're building larger and larger orbitals, and as a result, those electrons just simply aren't as close to the nucleus, and there's just not as big of an affinity for those electrons. Okay? So that's your next trend then. Electronegativity increases left to right, decreases going down that periodic table. All right, then our final periodic trend for our little introductory lesson here is that of metallic character. So remember, metallic character is all those properties that we typically associate with the metal, metallic luster, conductivity, both thermal and electrical, malleability, all these guys. And we saw how when the periodic table is laid out and we color code the different elements based on what kind of character they have, are they metallic, are they non-metal, or are they somewhere in between, we find that all the metallic compounds are grouped on the bottom left, right? So, metallic character is basically actually increasing as you go down this direction, and decreasing, of course, if you go the other direction, to the extent that if you go up to this top right corner, you actually have non-metals, okay? So non-metal compounds. So metallic character essentially does the exact opposite of electronegativity. So electronegativity gets highest going up here to fluorine, electronegativity, and we can write it in, get those in there. So increasing electronegativity as you go from left to right and from bottom to top on the periodic table. And in metallic character increases going the exact opposite direction, right? Going from right to left and going down that periodic table. So fluorine's the most electronegative, right? And right down here, our francium has the lowest electronegativity. And so then conversely, francium will have the highest metallic character, but then fluorine will have the lowest metallic character. Okay, so to sum things up there, we went through a number of topics here. So basically, we use this fact that orbitals increase in size with increasing n to draw out our first trend, which is a trend in atomic radius or size, which states that it increases as you move down or to the left on the periodic table. Right? We saw how atoms like to have a full outer shell, and the implications of this in terms of developing the octet rule. And we saw that atoms then in the same column on a period tend to form ions with the exact same charge. Then we looked at this concept of electronegativity as a tendency to attract electrons, and we saw that electronegativity increases as you move up and to the right on the periodic table. So the trend, our last trend that we looked at then is the trend of metallic character, which essentially is opposite that of electronegativity. Metallic character increases as you move down and to the left.